I would like to thank the organizers for giving me this opportunity to speak about some work I've been doing over the past couple of years. And I'll probably, if there's time, I'll talk about some ongoing work with people at PI and Caltech related to tensors. So let me start with the brief outline, very quick outline. In fact, I'll present a very brief introduction of the idea, what I really mean by these tensor networks and how they are based on this Lagrangian and the Hamiltonian. They have different manifestations based on partition function or the wave function, whatever approach you want to deal with. And then starting with the partition function approach, I'll talk about some real space renormalization group techniques and apply it to two-dimensional O2 model, three-dimensional POTS model, and then eventually move on to three-dimensional O2 model with finite chemical potential, which is a difficult problem for Monte Carlo. So for example, we want to study tensors. One of the advantages of using tensors is that you can study systems which have sign problem, for example, with topological theta term or finite chemical potential. So I'll talk about some of that. And then if there is time, I'll talk about MPS approach, which is like a wave function approach to discuss scattering of quasi-particles in Ising field theory. So if you don't know, Ising field theory is just a CFT perturbation by two operators, energy and spin operators. And it has a lot of interesting phenomena. And it is one of the most complicated integrable models known in physics. And I'll talk about it if I have time. Okay. So starting with different RG methods, there have been various renormalization group schemes, and some of the flavor of this you heard in Anna's talk, starting from Kadanov's spin blocking around 66, then Wilson RGs about 1975. And then the field was like, that nothing much happened for 17 years. And then there was this very interesting paper by Stephen White, and that is DMRG. And then again, after about 14, 15 years, there was another development in the field that instead of density matrices as used by White in 92 paper, the Levin and Nave in 2007 proposed that we can use an alternative description in terms of tensor to carry out the renormalization group or the coarse graining and study some interesting spin statistical models. And this was later extended to higher dimensional by the Chinese group in 2012, and then eventually Guy Vidal at PI came up with this tensor network renormalization, which is better suited to deal with critical systems. So for example, one-dimensional quantums, Ising chain and spin and things like that. While the previous methods like TRG and HOTRG fails when you are at criticality. Okay. So I just want to bring this section from Wilson's famous paper on Kondo problem. And he says that the fourth aspect of renormalization group theory is the construction of non-diagrammatic renormalization group transformation, which are then solved numerically using a digital computer. This is the most exciting part of the RG program, according to him. And this is exactly what we are doing now, but in a different way using tensors. And he used that method long time in 75 to solve the Kondo problem. And then he says that if you ever come up with some new method, the Ising calculation is only a practice calculation since the exact solution is known. So in the next, the advantage of tensor networks is that Rich showed three different methods for Ising model, like on a 2D lattice, square lattice. Tensor networks can solve Ising model in 15 seconds. So you don't even need to look at any cluster algorithms. They're much more powerful. You can reproduce Onsager's exact result up to an accuracy of 10 to the -7 for the free energy in the thermodynamic limit in 15 seconds on a laptop. So it's probably the best method we know today to solve spin models, at least in lower dimensions. The higher dimension is a different problem, and a lot of groups are working on that. So this is inspired by Wilson's paper in which we want to do numerical RG using some different methods, and in this case, tensors. So as I've already mentioned, it provides an arena for studying lower dimensional critical and gap systems faster and more efficiently than any other numerical method. Also, formulating in terms of tensors can enable us to study systems where the usual numerical methods such as Monte Carlo fail due to a sign problem. In addition, if you do a Monte Carlo, you can always only compute the expectation values. There's no knowledge of the partition function you get. But in this tensor networks method, you can compute the partition function also. So that is another advantage. This is based on the Lagrangian or the partition function approach. If you want to think about it in terms of wave function approach, then the Hamiltonian, the wave function approach can be useful to study real-time dynamics, which is what we want to do, because obviously, as we know that in Monte Carlo, we do this imaginary time, and for some of the problems, real-time is more suited. So this is what we do when we probably talk about the scattering in Ising field theory. Using the matrix product state to create quasi-particle wave packets, and then we'll collide those wave packets and see how the S matrix or the phase shifts look like in that theory. And also tensors are advantageous in the sense that the knowledge about tensors and in fact Mera and other networks has helped to understand ADS-CFT in the sense that there's some sort of a relation between them. So tensors have different advantages. As I've already mentioned, there are two different approaches based on Lagrangian and the Hamiltonian formulations. The one for the Hamiltonian, we consider wave function. So if we consider n spins, the Hilbert space is 2 to the n dimensional if the spin is up and down. But the idea of matrix product state is to represent this coefficient not by 2 to the n numbers, but by some order n numbers. And this can help us to study, say, for example, quantum spin chains effectively on classical computers, because we cannot obviously store the entire state. So we try to store whatever we have in order n parameters effectively, and then study the ground state properties or excited state properties. So this is a brief notation. I'll show some diagrams in the next slide. So this is a simple notation. If there's a blob with no floating indices, it's a scalar. With 2, it's a matrix. Otherwise, it can be a higher rank object. Tensor of some rank 3, for example, here. Then the contraction, for example, the matrix multiplication will look like this in this notation. And if you want to do contraction over the internal indices, say, for example, the 4 outside indices are free, all the internal indices are contracted. So these are the basic notation which will be used in the figure in the next slide. So this is the tensor notation, which is probably well known to most of you. So what is the standard tensor renormalization group method? The standard method is, the goal of this program is to approximate the wave partition function to the best we can. For example, we cannot probably solve it exactly in 3 or more dimensions, because it's apparently I've seen that it's computer scientists work classify this as an NP-hard problem or whatever. The best thing we can do is to approximate, and maybe in lower dimension it can be very close to exact result. So how does it work? For example, if we take 2-dimensional Ising model, for example, on a square lattice, it will have 4 indices like this: left, right, top, and bottom. And then what we do is we combine 2 of the indices together, say left and top, and the bottom and right together, and we get something like this. Or we can combine another set, which is sigma L, sigma R. So in this case, it's equal because for Ising model, there's some sort of symmetry of the initial tensor. Maybe you cannot do this process if the initial tensor is not symmetric and things like that. So once you, in this case, we can do, this is just a representation. And how do we go from this to this? We go from this to this by combining, making a matrix out of this rank 4 tensor, then doing a SVD, singular value decomposition, assigning a square root of S to one side and square root of S to the other side, and then combining it in this tensor. So you go from this to this, which is exactly what is shown. So this is a basic step of TRD, which was proposed by Levin and Nave in 2007. Then the method proposed in 2007 was restricted to 2 dimensions. Then there was some development after 5 years in 2012, and they argued that it is better to do a higher order singular value decomposition rather than a singular value decomposition. So higher order singular value decomposition is just like a generalization of some sorts of matrix SVD to tensor SVD. So for example, it's higher order SVD in that you have, instead of matrices, you have like higher rank objects. So that is higher order SVD. And using that, they found some interesting results for, say, 3-dimensional Ising model on a cubic lattice. They could compute the critical temperatures to some accuracy and things like that. So this method usually works in 2 and 3 dimensions, and some people have also applied this to 4 dimensions, but that is a little tricky, and I will not discuss anything about 4 dimensions. Now, this method performs is simpler than the TNR methods, which was proposed to deal with critical systems, because in TNR the complexity is much higher than what we have in this. So whenever we want to like be away from the critical point or don't want to deal with really a conformal field theory critical system, this is often a nice way to proceed. So I'm not showing anything about the Onsager result because it's probably well known. I just want to do this one single slide about Ising model with magnetic field. There's no exact solution known. The best we know is the solution of Ising model on a random graph with magnetic field, and this was solved famously in '86 by Kazakov and Bolotov by mapping to some Hermitian matrix model. But there is no solution for any regular lattice for the real values, especially real values of magnetic field. For example, there was this work by Yang and Lee in '52, well-known work, and Merlini in '74. They did it for some specific value of magnetic field, which is imaginary. And obviously the Onsager case is when H is 0, so Z is 1. So this is what they wrote down for this specific value of magnetic field. But if I ask you, if I ask what is F beta H, where H is just real, there's nothing known. So, but that is not a problem for tensor network methods because we just decompose the Boltzmann weight in a different manner. You can just do it again in 15-20 seconds, and this is what you get. This is the free energy versus beta for different values of magnetic field, starting from the lowest, which is here. So the exact result of Onsager will be something a little below that. And then you have different values of magnetic field. And there is no exact solution known. I like the solid lines which you see. So the blobs are the numerical results. The solid line is some guess I just had, and it's on that. So there's no exact solution known, or probably guess is all probably I can do. And obviously this is still an open problem. Let's just move to now to more complex spin model with continuous symmetry, unlike what we discussed before, Ising model with discrete symmetry. So if you look at this 2D O2 model, the Hamiltonian is given by this two terms. The second is the symmetry breaking term. And this is the well-known term. And this term can be represented, we can study this model using tensor networks by just doing a simple Jacobi-Younger expansion, which is like a Fourier transform of some sorts. And then we can expand this, and then it's like a strong coupling expansion, which we do often in QCD, and you must have heard about it in Anna's talk. So the basic idea is you write down the partition function, you do a strong coupling expansion, you construct the initial tensors in terms of that decomposition, and then you try to do coarse graining effectively and hope that at least you get to the right continuum physics or the long distance physics. So this is what we did for this case. This was the free energy versus temperature. This is how we compute expectation values in tensor networks. So for example, if this orange was just a blue blob, then it's just a partition function. And if there's an orange blob, it's corresponding to some magnetization. If there is some purple blob, it will correspond to some other expectation values. So this is the way in which the tensor networks are contracted, and this expectation values are computed. In this case, for example, in the previous slide, you saw that there was a Bessel function and there was this condition that's just corresponding to the O2 symmetry of the model. So if H is equal to 0, then this picks up a condition that I plus K must be equal to J plus L. So incoming flux of some sorts of U1 charges should be equal to the outgoing. This is corresponding to the U2 symmetry, O2 symmetry. And this model was interesting for us because this has this famous BKT phase transition, which is unlike any of the transition we usually see in statistical systems. None of the derivatives of the free end is continuous. So it's like if you compute any derivative of this, numerical derivative of this, you cannot see the sign for phase transition. But what is interesting is that there are other ways in which we can detect this phase transition. And this phase transition, it was studied in the 90s by using Monte Carlo methods and other methods. But obviously, we want to study it using tensors, and this was what we did. And for that, what you want to really do is you want to introduce a symmetry breaking field, and then you want to compute the magnetization for different values of symmetry breaking field, and you want to take the limit of vanishing external field. So you do it for different values of H, and then you compute the susceptibility, and then you compute the critical temperature for a range of values of H, and then you extrapolate to zero limit, and this is what you get. the result we get is consistent with what was obtained like 10 years ago using Monte Carlo. So most of these were done using Monte Carlo from 92 on until 2013, where this new method suddenly started, people started using this and exploring this, and this has seemed to be very useful. In addition, I should mention that even though I'm not showing anything about that, the critical exponent delta, which is 15 in this case, well-known critical exponent, has been computed for 2D O2 model. You get a number which is 14.9 plus minus 0.2 or something like that. So tensor networks have been able to do that as well. Now, if we talk about moving to 3 dimensions, it's harder, obviously, like most of the problems in physics, where everything works in 2D, and as you soon go to 3D, things doesn't seem to work that well. But in this case, mostly the problem is that the prescription which we use in 2 dimensions doesn't work that well, because there's always an associated error, even in the 2 dimensions case. But in 3 dimension, what happens is the errors grow much more obviously than 2 dimension. That is one of the reasons. There's also growth of entanglement that happens much more in 3D with increasing dimensionality. And you have to use some really well-defined prescriptions. For example, when you want to do a 2-dimensional statistical system, you introduce something called a disentanglers, which are part of Mera network and things like that. What they do is they just reorient the local Hilbert space in such a way that the errors as you coarse grain doesn't increase. In this case, in 3D, one has to do some similar things, like introducing some additional transformations, which will keep the errors under control. But it is very hard to do in 3D, and no one has been able to do it yet. And obviously, the third point is that the computational time obviously scales as 4D minus 1. So if you go to D equal to 3, it's obviously much harder compared to 2D. So, and you can see from these pictures I've drawn here, so each of the yellow is a rank 6 object. And then once you want to do one step of coarse graining along, say, in the YZ plane, you compute this projectors UX. So you have to do these SVD, and those SVDs are very expensive. So that is the bottleneck in these higher order computation. But there was a development about which you will hear more in next week's lectures by Daisuke Kado, in which he came up with this idea that maybe what we can do is, like often in physics, when you have a problem, you want to decompose the problem and deal with the smaller parts. So this was the triad decomposition. What he said, what he did in his paper was, let's not worry about this rank 6 object, but let's just decompose it into, say, triads, 4 triads in this case, and then deal with these objects, which are smaller. Probably you have to do a little more computation time, but memory wise and otherwise much more efficient. So there's this decomposition of this tensor diagram into this diagram, and this T here is equivalent to this product of ABCD, and the dashed red are the internal indices which are summed over. So once we deal with this triad approximation, some of the problems becomes easier, and I applied that to study O2 model with some collaborators, then applied that to study large Q POTS model, and there are many other problems which probably can be accessed by this technology. It is not as accurate as the other methods, but it's like a trade-off you do for the accuracy and in higher dimension. Okay, so I'll just quickly talk about this 3D Q state POTS model. I was interested in this because in 2D POTS model, the exact solution of the critical temperature with the Q or the state is known. But in 3D, there's only single Monte Carlo work which focused on this range of Q between 3 to 10. So there was nothing in the literature more than for say large Q system or Q state with large Q with Q greater than 10. So we studied this using tensor networks, and the shaded region is the results we obtained using the tensor network methods, and the unshaded blue dots are the one which is from the Monte Carlo. And it seems to follow a nice parameter dependence, but the expression is still unknown. It's an open problem to find the expression for 3D POTS model. And you can see about, you can read more about this in the famous textbook by Baxter from 82, if you're interested. But for 2D, we know everything, this expression is known, but unknown for 3D. Okay, so this system, obviously, the dimensionality of the Hilbert space, we're not talking about the Hilbert space language, but we're dealing with the partition. The dimensionality is q to the n, where q is some number which is shown here, probably, which is shown here. And this is a discrete symmetry, ZQ symmetry. Now we move to a little more complicated model, which we studied last year. Okay, which we studied last year using Monte Carlo methods. So the motivation to study this model was to have a third approach to this problem. There are two currently existing methods which compute critical exponents in 3D O2 model. One is the Monte Carlo and the conformal bootstrap. So for example, conformal bootstrap folks compute this charge zero scalar, which is related to the critical exponent nu by this. And then nu is related to the dimensionality and the alpha coefficient like this. Alpha is just the divergence in the specific heat, which we can measure on the tensor network computation. So for example, the ideal scenario will be to do a computation of alpha using tensor network computation and then see what you get for nu and then compute it to the delta S computation from conformal bootstrap. So that was the goal, but I realized that it's very hard to at least compute the critical exponents for this model in 3D using tensors at the moment. And we studied only some thermodynamical observables and computed the critical temperature for a cubic lattice. And what we are trying to do now is we are trying to use some GPU acceleration so that maybe we can do a little higher, little better, and maybe get closer to the critical exponents. But I'm pretty sure in the next 3-4 years, it will be hopefully be possible to do. So these are the results we got for this. This is the energy versus inverse temperature. This is the specific heat. You can see that there's a well-defined peak corresponding to this continuous phase transition around the value which we expect. And this is for the magnetization. As you go to the small field limit, it coincides with this. But this could all have been done with Monte Carlo also. But what we could not have done using Monte Carlo is computing the particle number density, for example, which is denoted by rho, given by dl and z by d mu, for example. And there is very interesting phenomena known as silver blaze phenomena. In Lattice QCD, people know about this. And this the silver blaze phenomena is just that even though you have mu in the partition function, it doesn't affect the if you compute rho, it is 0 until some point, and then it becomes non-zero. So for example, there are different colors here indicating different values of beta. And as you move from 0.42 towards the critical temperature, so this is a gapped system. So you expect that the mass of the lattice excitation will be some finite is a number. And that's why you see that it is non-zero until some point. And as soon as you get close to that critical point or get close to that transition, it starts, there's no value of mu for which rho is independent of mu. So for example, because it's going to a gap, tending towards a gapless system. So this is what we studied. One thing to note is that we can never get this plot using Monte Carlo. So this is one of the advantages of using tensor network method. We don't have time. So yeah, we don't have time, but I'll just quickly mention that now what we're trying to do is we are trying to look into this MPS approach. So this is the classic Hamiltonian of this quantum Ising spin chain. What we're trying to do is that this model in the field theory limit, there are two integrable points of this model. One is known as the free fermion model, and one is the E8 limit. And E8 limit was solved famously by Shasha-Jamalnichkov, and he computed the spectrum which consisted of 8 particles, in fact, and out of which 3 are stable below the threshold, and 5 of them are stable because of integrable model. It drew a lot of attention. Popular Science article did a one-dimensional magnet detect a 248-dimensional Lie algebra, which is E8 theory. This is the lower. It is not exactly E8, but it has some like properties in the whatever spectrum we have seen like E8. So there are different number of stable particles in the magnetic field and tau plane. Just want to remind you that tau is T over Tc minus 1. So tau equal to 0 is T equal to Tc. So you can go along this direction, go along this direction. This place is the free fermion limit, and close to this is the E8 limit. And there are different number of particles as you go along that curve. So what we want to do is it has a rich spectrum, and there's very famous argument by Subir Sachdev who says that this is the most complicated integrable model. You can just see that it has 8 stable particles, and these are the masses. It's like it's very tricky. integrable model. What we really want to do, it has a mass dependence on the magnetic field goes something like this, and we did MPS computations to see that we exactly get that. So the mass of those stable particles are all proportional to some fractional power of h. That is exactly what we see. And then the idea is that we want to interpolate between two S matrices. So if we look at the S matrix around the free fermion, it is -1. If we look at the S matrix around E8, it is 1. How does it interpolate between two limits is an open problem. And it's open problem because there's no tool available to study that strongly interacting quantum field theory in a real time, but we are using tensor network methods to deal with that problem. And yeah, this theorem came up in Martin's talk, so I just added this line. In 2 dimensions, there can be a possibility that the 1,1 to 1,1 scattering can be elastic in the sense that there's no particle production, but it's not true in higher dimensions because of this theorem. So we indeed see a lot of cases where the particle production is 0. And obviously, if you go to the, as you go along the h tau plane, you find parameter space regimes where it is obviously there's particle production and there's inelastic channels which open up. So this is work in progress, and we should have it out soon. And I'll thank you.
Thanks, Raghav. There is time for questions, and I see a question coming straight up.
Can you do triangular lattices and hexagonal lattices?
Using tensor network methods, people have looked at that. Yeah.
What?
People have looked at that. You can do 2D Ising on triangular. People have done that.
Yeah, so it would be interesting because you have an exact identity between the two. So in one case, you would have a 6-fold vertex. In the other case, you have a 3-fold vertex.
Yeah.
And
I think in the original paper, if you look at the original PRL paper by Levin Nave, they do it for triangular lattice. Ising model on a triangular lattice.
Right, but it's actually, there's exact equations, which I wrote down. They're well known.
Oh, one can check it, yeah.
Right, so first of all, you could check that that both of them gave the same answer.
Yeah.
Which would be interesting. And then you could also vary the couplings, and you have this whole critical surface for skewed.
Yes.
So you could see whether you could actually see the modular plane.
Yes.
And since now this is all known exactly, it would be a really great way to test your thing. I mean, the 6-fold thing is like your 3D thing.
Yeah.
And the hexagonal lattice is even simpler. It's trivalent.
Yes.
So it would be.
I think people have done like Ising model on using tensor networks on Sierpinski carpet.
Right. I'm just saying now that we have this whole critical surface, you would have to do it with asymmetric couplings, which presumably is not really changing things in your formula, right?
Yeah, probably you can still see the basic idea. Yeah, you can still do it. I think.
You just have to know which is up and down and right and left.
Yes, yes, absolutely.
So it'd be very amusing.
Asymmetrical couplings can be.
It would be a good way to test all your methods because you have a whole surface and you have an exact duality and between 2 different methods. It'd be fun, actually.
Okay, yeah, that sounds like
right. Actually, if you do it, tell me about it. It'd be fun.
Yeah, if I get time, I'll definitely do it.
Can I ask a question?
Yeah, sure.
What is the meaning of growth of entanglement? It is like when you are moving forward in time, then more degrees of freedom of subsystem entangle with its complement.
Yeah, so think about growth of entanglement in terms of, say, for example, think about the matrix product approach. The matrix product approach is based on the fact that you have a local Hamiltonian, right? So you set out some neighborhood and you say that, okay, fine, this is the neighborhood of interaction. So there's always some entanglement which comes in because you cut in some region of, say, if you have a quantum spin chain, you cut in some region, there's some entanglement which you get, right? If you do it in higher dimension, the same prescription, the growth is much more in the sense that sometimes it's like depending on what kind of system you're dealing with, gapped or critical, like can be volume or area dependent and things like that. So that process is related to the truncation because we are not doing anything exactly, right? We are making this approximation that the Hamiltonian is local. If it is not local, and if it is, you're losing a lot of information, then that renders the RG process inefficient. So you can never know whether you are converging to the right fixed point, for example. There are also some fictitious fixed point like corner double line fixed point and things like that. So it can become really tricky. In 2 dimensions, it's still okay because you have a lot of computational power now, and you can still like crank up the bond dimension and get really close. But in higher dimension, it becomes much harder. And that is why the progress has been very slow.
So it is happening when you are going from 2D to 3D, or you are living in the fixed dimension.
Yes. So
Is it happening when you are going from 2D to 3D, or this?
No, it happens when you go to higher dimensions,
Okay.
because the SVD process and everything else which we do in the tensor network, like everything accumulates error, and then it, like at some point it breaks down. At least you cannot get critical exponents, for example, very accurately at the moment with this method.
Suppose we are living in 3 dimensions, then it can happen, or we have to go to higher dimension, then entanglement growth will happen.
No. So it's always relative to something. So for example, what I'm saying is compared to 2 dimension, it's more in 3 dimension.
Okay.
So it depends on what system you want to study. If you want to study 4 dimensions, you have to deal it with it much more than 2 and 3 dimension. So that's what the thing is, that computational time and growth, everything grows with dimensionality.
Okay, thank you.
It's harder.
So the decomposition shown in Triad 1, is it unique or?
No, it's not unique.
It's not unique.
No, you can do the decomposition, and the triads can be, you can make an, this is one of the choices you can, this is one of the way you can break it. There might be other optimum ways of breaking it, but probably Kado will talk about that in his talk, but I think he's working on that. But for me, the simplest one for the moment was, because I just want to play around with this and see what are the theories I can understand. For example, 3D O2 model, no one has studied before using tensor networks, and more so at finite chemical potential. So this is like a new tool we have. For example, I don't even know whether complex Langevin methods has studied 3D O2 model and seen the silver blaze phenomena. If they have not, then this is the only method. If they have, then there are 2 methods. So it's interesting in that way. Yeah, I think Kurt Langfeld studied this using some, I don't know what method. He was looking at the quantum limit of 3D O2 model. What was the method he used? Some cluster, I don't know. I don't remember that, but there was a paper there's a paper which studied that. So yeah. No, not the density of states method, some other method. I'm not sure. I'll check and maybe we can discuss later. Any more questions?
I had one. If there's
Yeah,
no one
sure.
else, I can take over. There's a couple minutes left before the tea break, but talking about the 3D POTS model,
Mhm.
I was reminded that the 3-state 3D POTS model has been a crude approximation to finite density QCD.
Yeah.
And I wonder if that non-zero net particle number or finite chemical potential is something that you can incorporate into or have
Yeah,
incorporated.
that's a very good question. Yeah, I can definitely do finite chemical potential.
So 3-state POTS model.
3D
So
3-state pot model.
heavy dense QCD.
It's a first order transition. It has first order transition, right? Yes.
But as a very crude model of finite temperature QCD,
Yes.
look at the heavy quark limits, you get Polyakov loops, replace those by the Z3 center symmetry, you get 3 states that you can then approximate by a POTS model. So for many years, that was a cheap way of looking at exploring finite density methods in a much simplified system that has some path to connect it to QCD. So it might be interesting to look at.
It
with
has
this new
weakly
approach.
first order, like it gets more strongly first order as Q increases, but Q equal to 3 is, I think, the boundary line, because Q equal to 2 is continuous.
If you
Q
have,
star is 2.45 in 3D, like the optimum value where the nature changes, but Q equal to 3.
so several interesting things to look at. A last call for questions before the break. And not seeing any, let's thank Raghav again, Richard.
Thank you.